In this video, we take a look at Gay-Lussac's law. Gay-Lussac's law is another one of the gas laws that we're learning about. Remember that with the gas laws we've learned so far, and the same with Gay-Lussac's law, is that mass is constant. All right, so we're not changing the number of particles that are there or the amount of the substance. It's still the same amount of gas you start with. All you're doing is you're changing the conditions. This time, Gay-Lussac's law looks at pressure and temperature, which means then that we also have to have a constant volume. Okay, so it's got to be, if you're dealing with a gas, in something that's rigid so the volume can't change. Okay, so this is important when we're dealing with Gay-Lussac's law. So Gay-Lussac's law says that at a constant volume, the pressure is directly proportional to the temperature. Okay, and if you look at the graph, as pressure is going up, so is the temperature. That's why we see this nice relationship here, right? And notice temperature is in Kelvin again. So when we're dealing with these gases, our temperature we're going to be dealing with in our calculations needs to be in Kelvin. So from this relationship of pressure directly proportional to temperature, we can develop an equation that P equals K times T. And again, just like before, this K, this constant doesn't matter. We don't calculate anything of the K, but knowing that that constant is there is what's important because it allows us to look at this particular scenario. When we rearrange it, we get P divided by T equals this K. And if we're at one set of conditions, we know that by changing the pressure and temperature conditions, it still has to equal the same K value for that gas. So when we're dealing with this, we tend to use Gay-Lussac's law when we are comparing two different conditions. So if we take that gas and we have it under one set of conditions, we'll call it 1. Our K1 value has to be the same for that gas if we change the conditions to now whatever conditions 2 would be. And then we can set up this relationship. P1 over T1 equals P2 over T2. Right? And this is what we use when we're doing things using Gay-Lussac's law. We're really using it to see how does this gas, when we go from one set of conditions to another, how does it behave? Knowing that pressure has to be proportional to that temperature. So let's try a calculation using this idea of Gay-Lussac's law, the relationship of pressure and temperature. So in this example, Mr. Warner placed 502 liters of gas in a rigid container and sealed the container. The initial pressure inside the container was 75.2 kPa. Mr. Warner then applied heat to the container and the temperature rose to 374 degrees Celsius. The pressure rose to 168.3 kPa. What was the initial temperature of the gas in degrees Celsius? So let's take a look at the info that's in here. We have a volume. Now let's figure something out about this volume. The volume is 502 liters, but it says it's a rigid container, so this is going to stay constant, right? We're not going to change that because it's in a rigid container. So we don't need to do anything with the volume. We can just now work with our pressure info and our temperature info. So our pressure, our first pressure condition was 75.2 kPa. Then it gave us the temperature that it rose to. So that's our second temperature. It would be 374.0 degrees Celsius. And our first temperature, we don't know. The other piece of information we know is the pressure in this new condition when it's been heated, and that's 168.3 kPa. So this is the info that we know, and just like previous questions, when you're dealing with these gas laws, we need to convert our temperature into Kelvin. We can't be working with degrees Celsius. So we're going to take this 374 and add 273 Kelvin to it, and you will get 647 Kelvin. So now we've got the right unit for temperature. We can do our calculation. So we know P1 over T1 equals P2 over T2. So we know P1 times T2 over P2 has to equal T1. So when we go and sub in the numbers now, I've got 75.2 kPa and a temperature of 647 Kelvin. And my other pressure was 168.3 kPa. So there's my numbers put in. I'll punch it into my calculator, in my handy dandy calculator, and it will spit out 289.09 Kelvin. But we want this in degrees Celsius, so now we just have to go and subtract 273. So we're going to do that conversion. We're just going to subtract 273 and we'll get 16.1. We want to stick with 3 significant digits, so 16.1, and that would be degrees Celsius now, right? So we've done that conversion. That conversion to degrees Celsius, and we end up with that unit of degrees Celsius with our work. Notice again, if you're looking back at the calculation, kPAs end up canceling out. That's how we ended up with Kelvin there, and then we converted to degrees Celsius, and now we know what that temperature is. And if you sit and think about it for a second, this is the nice part about these gas law problems. If you actually think about what's happening to this gas, we know because pressure and temperature are proportional to each other, that if the pressure from one scenario to the other has gotten lower, the temperature should get lower. So I should see a temperature lower than what I started with. If I finished at 374 degrees Celsius, we had to start with 16.1 degrees Celsius. That makes sense. It's a lower temperature, right? And that occurs when we have that lower pressure. So if you think about these problems for a bit, sometimes you can check and see if you've done the calculation correctly. Because if we had gotten a much higher temperature than 374 degrees Celsius, we should recognize pretty quick that there would be something wrong. So don't be afraid when you're done your calculation to sit and think about it for a second.